Have you ever just looked at a messy bookshelf and thought, okay, what is the best way to organize this? By author? By color? Maybe by height? Well, in the digital world, we face that exact same problem all the time, but on a scale that is just mind-boggling. We call it sorting, and believe it or not, it's one of the absolute cornerstones of computer science.
So let's just get right to the big question, right? If all we want to do is get a list of numbers from smallest to largest, or a list of names from A to Z, why on earth are there so many different sorting algorithms? I mean, shouldn't there just be one best way to do it and we can all call it a day?
Well, the short answer is nope. There really is no single best way. You know, choosing a sorting algorithm is a lot like picking a tool from a toolbox. You wouldn't use a sledgehammer to hang a picture frame, right? Every single algorithm has its own special set of strengths and weaknesses, its own specific trade-offs.
And to really get a handle on these trade-offs, we first have to look at the kinds of problems we're actually trying to solve in the real world. Because these problems, they come with their own rules of the game, their own limitations, what we call constraints. Okay, think about this for a second. Your social media feed. New posts are popping up constantly, every single second. You can't just pause the entire internet and wait for every post to come in before you start organizing them. You have to be able to handle data as it arrives, piece by piece. And this is a perfect job for what we call online sorting. Algorithms that are built for this, like a classic called insertion sort, are absolutely perfect. So imagine you've already got a sorted list. When a brand new item shows up, insertion sort just finds the right spot for it and slips it in. You don't have to resort the whole thing from scratch. It's super efficient and it works in real time.
All right, here's another classic constraint. Let's say you've got a big spreadsheet full of students and you've already sorted them alphabetically. Now, you decide you want to sort that same list by their final grade. But what happens if two students have the exact same grade? Do they stay in their original alphabetical order, or does the new sort just scramble them up randomly?
This little property, it's called stability. A stable sorting algorithm gives you a guarantee. It promises that if two items are identical, like those students with the same grade, their original order will be preserved. And this is a huge deal. Notice on the slide, an algorithm like merge sort is stable, but another really popular one, quicksort, is not. That's a critical trade-off you might have to make. Now for a big one, resources. I mean, what if you're trying to sort data on a tiny little sensor out in a field, or maybe on a smartwatch with barely any RAM? You can't just go around creating huge temporary copies of all your data to help you get the job done. You literally don't have the space. And that leads us to this idea of in-place sorting. The best way to think about it is like sorting a deck of cards entirely in your hands without needing a big dining room table to spread them all out. An in-place algorithm sorts the data right there within its own little box, its original memory space. And this slide just lays it all out, right? It's the choice you have to make. On the left, you've got these super memory-efficient algorithms like heap sort and quicksort. But on the right, you've got powerhouses like merge sort, which, to do its magic, needs to create a whole temporary copy of your data. And that extra memory, well, that's a pretty significant cost. Okay, so we've covered all these different rules and constraints. But let's be honest, a lot of the time, all of those things take a backseat to the one metric that often matters most, pure raw speed. In computer science, we measure speed with something called time complexity, or you'll often hear it called big O notation. Now, don't worry about the math. All it's really asking is a super simple question. As my list gets bigger and bigger, how much more work does the algorithm have to do? Does the workload grow kind of slowly, or does it just explode into a total nightmare? Now, this table is fascinating because it shows this huge performance gap. You've got algorithms like selection sort that are in what we call the O of n squared category. Let's just call that the slow lane. O of n squared basically means that for every item on your list, the algorithm has to look at every other item. Then you've got the real workhorses, like merge sort and quicksort, in the O of n log n category. This is the fast lane. And the difference between them isn't just small, it's staggering. And this chart shows you exactly why that matters so much. See, for a small list, the difference is, it's not that big of a deal. But when you start sorting millions, or even billions of items, the amount of work for an O(n) squared algorithm becomes astronomically huge. It becomes practically unusable. The O(n) log n algorithms, on the other hand, they just scale beautifully. So this brings us to what is arguably the superstar of the sorting world, quicksort. In the real world, on average, it is often one of the absolute fastest algorithms we have. It's smart, it's efficient, and it is used everywhere. And a quick look at its profile here shows you why it's so popular. I mean, excellent average time complexity, and it's super efficient with memory. But, hang on a second, look a little closer. See that worst case time? It says ON squared. That's the same as our slow lane algorithms. How is that even possible? Well, here's the catch. Quicksort has an Achilles heel. The way it works is by picking an element, called a pivot, and then sorting everything else around it. Now, in a totally random list, this is lightning fast. But if you happen to give it a list that's already sorted, it ends up picking the worst possible pivot every single time, and its performance just completely collapses. The high-speed champion suddenly finds itself stuck in the slow lane. It's a rare scenario, for sure, but it's a dangerous one you have to know about. All right, so we've got our constraints like memory and stability, and we've got the race against time. We now have all the pieces of the puzzle. We are ready to make a smart decision and pick the right tool for the job. Think of this as your final dashboard. You can see all the trade-offs right next to each other. So let's say you need guaranteed fast speed and you need stability. Well, merge sort is your answer, but only if you have the extra memory to spare. Or what if you're on a device with almost no memory, but you still need that reliable speed? Well, then heap sort is a fantastic choice, as long as you don't need stability. See how it works? And that brings us right back to where we started. The hunt for the single best sorting algorithm, it's just asking the wrong question. The real skill is in understanding the problem you're trying to solve, analyzing all of its constraints, and then picking the algorithm whose trade-offs are the best fit for your needs. So, the next time you see a sorted list on your screen, your search results, your contact list, maybe a music playlist, just take a second. Think about the trade-offs that were made behind the scenes. Was speed the #1 priority? Was memory a major concern? Was stability absolutely essential? That silent, invisible choice of a sorting algorithm is right there, working in the background, making your digital world just a little bit more orderly.